In the following moles and titration question taken from the ATP paper for O levels, the question is about finding the water of crystallization in a hydrated salt. So the question reads that the formula of iron 2 sulfate crystals is FeSO4.xH2O, where this, let's underline that, so where this X is the number of water molecules attached to each FeSO4 compound in the salt, where X is a whole number, it's also a whole number. So a student is asked to determine the value of X using 0.02 mole per decimeter cube potassium magnate, which is magnate 7, and this was called solution G. So this is KMnO4. Potassium magnate is KMnO4, and it's a very powerful oxidizing agent. So this titration is a redox titration. The first part of the question states that sample of iron 2 sulfate crystals was added to a previously weighed container, which was then reweighed. So calculate the mass of iron 2 sulfate crystals used in the experiment. So you're given table is given where the mass of the container plus crystals is given as 12.38 grams, and the mass of the empty container is also given, which is 5.42 grams. So if you want to figure out the mass of the iron 2 sulfate crystals, you just simply need to subtract the two values, get rid of the mass of the container. So if you subtract 12.38 from 5.4 and 5.42, the answer that you're going to get is 6.96 grams. So that is the amount of crystals that is present in the container. So that's the first thing. So let's write that down, note that down. The mass of the hydrated crystals that are being taken in the experiment are you have 6.96 grams of these hydrated crystals. Moving on to part B. The question reads that the sample was dissolved in 100 cm3 of dilute sulfuric acid. So the crystals are dissolved in 100 cm3 of dilute sulfuric acid, and the solution was made up to 250 cm3 with distilled water, and this was called solution H. So we're going to sketch those steps now. So here is my volumetric flask, and I'm going to make a 250 cm3 solution, which is going to be called H. The first part is that this is dissolved in 100 cm3 sulfuric acid. So you're dissolving 100 cm3 of sulfuric acid, which is H2SO4. So you're dissolving it in 100 cm3 sulfuric acid. Then you add distilled water to dilute the solution. So you're adding distilled water to make a more diluted solution. Eventually you're going to get a 250 cm3 solution, and that 250 cm3 solution is now called, the name of the solution is H. He's given the name of the solution. He's calling the solution H. So this is our solution H, and H is basically FeSO4 aqueous. Remember that sulfuric acid over here is only being used to dissolve, because sulfuric acid, H2SO4 and FeSO4, they're not going to have a reaction with each other. So it's only being used to dissolve this salt over here. So once this salt dissolves, so basically you have FeSO4 in the aqueous state, plus there would be some acid in the solution as well. Now in the next part, 25 cm3 sample of H was measured into a titration flask. Remember, we made a 250 cm3 sample of H, solution H. Now what he's doing is that 25 cm3 sample of H was measured into a titration flask. So we are transferring 25 cm3 of H into a titration flask. So here is my conical flask, which is also called a titration flask, and I'm going to transfer 25 cm3 of this FeSO4 into this flask. So only 25 cm3 H is being transferred into this flask. And remember, H is basically FeSO4 aqueous. So we took a tiny amount of the 250 cm3 solution. Originally we had a 250 cm3 solution, and we are just only transferring 25 cm3 of that solution into this titration flask. So and the next part is that solution G was run from a burette into the flask containing H until an endpoint was reached. So I now have to make a burette. So there's supposed to be a burette over here, which is going to be filled with G. So here's the burette, and I'm going to fill it with solution G. So filling it with G. G is K-4, potassium magnate. Remember, G was given. The information about G was provided in the second line of the question, where 0.02 mole per decimeter cube potassium magnate, and this was called solution G. So it's given over here. So we're filling the burette with G, which is K-4, which has a concentration of 0.02 mole per decimeter cube. So we're given the concentration of the solution as well, and G was run from a burette. So this KMNO4 is now being added into the flask, and so it's going to be added drop by drop, and it's going to react with the FeSO4 that's present in the flask over here. So potassium, and he's given us that potassium magnate is purple, so it's a purple colored. KMNO4 is purple in color, and you're being asked what was the color change at the end point. So what was the color in the flask? The color in the flask initially contains FeSO4. Now remember, FeSO4 is a green solution, or it's a pale green solution. So it's a green colored solution. So initially this flask contains this green solution. So your initial point, the initial color is that the solution is green in color. And when you start adding KMNO4, KMNO4 is purple colored. When you start adding KMNO4 into this flask over here, what happens is that KMNO4, when it reacts, it changes from purple to colorless. So as long as there is FeSO4 present in this flask, this purple colored KMNO4 falls into the flask and it goes colorless. So as long as the reaction is happening, KMNO4 remains colorless. It changes from purple, it reacts and changes to colorless. But as soon as all the FeSO4 gets used up, that's the end point of the titration. So when all the FeSO4 is gone, all of it gets used up, it reacts with the KMNO4. If you still keep on adding KMNO4, KMNO4 has nothing to react with, so it would remain purple, and that purple colored KMNO4 would make this solution go purple as well. So your final endpoint is when you start seeing purple colored KMNO4 in the flask, that would mean that the purple colored KMNO4 has nothing to react with now, so it's going to remain purple. So your initial color was green because of FeSO4, and when you start adding KMNO4, and when KMNO4 goes in excess, it's going to turn the flask purple in color. So that would indicate that you should turn off this tap, stop adding KMNO4 into this flask, because now the titration is complete. And in the next part, he's saying that 3 titrations were done. The diagrams below show parts of the burette before and after each titration. So 3 separate experiments were done. We're basically interested in figuring out what amount of KMNO4 was actually added into the flask. And he's doing 3 separate titrations. Remember, the 3 separate titrations are done to improve the accuracy, because doing more experiments and taking out the average would give you more accurate results. So 3 separate titrations are done, and the burette diagrams for each titration are drawn over here. So if you have a look at the burette diagrams, if you look at the first titration, and we're talking about the KMNO4 that's in the burette over here, and we want to figure out what volume of KMNO4 is added into the flask. So if you look at titration 1, the 2 separate burettes are drawn. The first one is the initial burette reading, which shows that initially the burette was filled up to the 0 centimeter cube mark, and this over here is your final burette reading, which is 25.90 centimeter cube. Now the amount of KMNO4 or G that's added is going to be the difference between the 2 values, because initially it was filled to the 0 centimeter cube mark, and after the titration the reading was 25.90 centimeter cube. So that would indicate that the amount of KMNO4 that's added is going to be the difference between the 2 values. So you're given a table as well, and we need to fill these values in the table. So the first titration, for the first titration, the initial burette reading is 0.0 centimeter cube, and the final burette reading is coming out to be 25.90 centimeter cube. So the amount or volume of solution G that's actually being added is going to be the difference between the 2 values, which is going to be 25.90 centimeter cube. So this is for the first experiment, the first titration. Moving to the second titration, if you look at titration 2, the initial burette reading over here is 23.30 centimeter cube, and your final burette reading is 48.60 centimeter cube. So I'm going to fill the burette, fill the table given below with these values. So your initial burette reading was 23.30 centimeter cube, and your final burette reading is 48.60 centimeter cube. Remember to take readings up to 2 decimal places, because that's the accuracy of a burette. the amount or volume of G that's added is going to be the difference between the two values. So if you subtract 48.6 from 23.3, the answer that you're going to get on your calculator is going to be 25.30 centimeter cube. And similarly, let's note down the values for the third titration. The initial Bureau reading is 6.90 centimeter cube, and the final burette reading is 32.40 centimeter cube. So that's 32.40 centimeter cube, and I'm going to add these values to the table as well. So the initial was 6.90 and the final burette reading gave us 32.40 centimeter cube. So the volume of G that's added is going to be the difference between the two values, which comes out to be equal to 25.50 centimeter cube. Now the next part in this row over here, you have to take the best titration results, and remember the best titration results are the ones that are close together, because they show if the values are close together, that would indicate that they are consistent. So this value is slightly off. It's slightly away from the other values, which means there must be something wrong going on in this titration. So I'm going to take these two values because they are very close to each other. So these are my best titration results. The second and the third titration are giving me the best titration results. And after taking the best titration results, use these results and find the average volume of G which was used. So based on these results, I have two values. One experiment says that 25.3 cm cube is used. The second one says that 25.50 is being used. So if I take the average and I divide by 2, add them up and divide by 2, the average volume of G that's being used is it's coming out to be 25.40 centimeter cube. Now this here is the average volume, which is 25.40. So this is the amount of KMNO4 that's being added. So I'm going to write this value over here. The volume of KMNO4 that's being added is going to be 25.40 centimeter cube. So this the burette readings were given. So that's the amount of KMNO4 that's being added into this flask. Now, if you look at KMNO4, you're given the concentration, you're given the volume as well. So using this information, you can find the number of moles of KMNO4 in the burette that are being added into the flask. So moving to the next part precisely states that he's given us that G is 0.02 mole per decimeter cube KMNO4. Calculate how many moles of KMNO4 were present in the titrated volume of G. So that's the volume of G that's being added, and that's the concentration of G. So using the formula for moles in a solution, moles is basically equal to concentration multiplied by volume. The concentration is given, it's given as 0.02. And the volume that we calculated in the previous step, the average volume of KMNO4 that's being used is coming out to be 25.40 cm cube, and I need to divide that by 1000 to calculate a value, to give a value in dm cube. I need to convert that in dm cube. So the answer that I'm getting for this part is going to be, it's going to come out to be equal to 0.00508 moles. So that is the amount of moles of KMNO4 that are being used. So I'm going to write these moles of KMNO4 over here in the sketch over here as well. So the amount of moles that are being added are 0.0000508 moles. So that's the quantity of KMNO4. Let's circle it. That's the quantity of KMNO4 that's being, so that's the quantity of KMNO4 that's being added into the flask over here. Now in the next part E, the information that's given is that 5 moles of FeSO4 react with 1 mole of KMNO4. So the ratio of KMNO4 reacting with FeSO4 is given. And he has said that 5 FeSO4 moles react with 1 mole of KMNO4. So that's the ratio. So we are basically doing a titration where KMNO4 is reacting with the FeSO4 that's present over here. And the information that's given to us is, the information is that 1 mole of KMNO4 ends up reacting with 5 moles of FeSO4. So it's 1:5. So if 1 mole reacts with 5 moles, we are adding 0.00508 moles. So how many moles of FeSO4 would be present? So the amount of moles would be 5 times this quantity over here. 1 reacts with 5, so 0.00508 moles of KMNO4 would react with how many? So I'm going to use ratios now. So 1 reacts with 5. So if you have 0.000508 moles, then how many moles of FeSO4 would react with it? So using simple ratios, the answer would be, it would be 0.000508 multiplied by 5. And the answer that I'm going to get for this part is going to be 0.0. It's going to come out to be 0.00254 moles. So that is the quantity of FeSO4 that's present in this flask. So we should write that down as well. So the quantity of FeSO4 that's present is 0.00254 moles. And I'm going to highlight that. That's the number of moles of FeSO4 present in this flask over here. Now moving to the next part, part F. You're now supposed, you figured out the moles of FeSO4 in this flask over here. So we have figured out the moles of FeSO4, which are coming out to be 0.0254. So in the next part, he's asking calculate how many moles of FeSO4 present in the 250 cm3 of H. So remember, when we were titrating, we just took a 25 cm3 sample of H. Now he's asking what's the quantity of moles of FeSO4 in this 250 cm3 H that we originally made. And we took 25 cm3 and did the titration. So if 25 cm3 contains 0.00254 moles, so what would be the quantity of moles in this 250 cm3 in this larger container? So what would be the quantity of moles in this? So it's simple ratios. So 25 cm3 volume contains these many moles. So 250 cm3, that's 10 times the volume, would contain 10 times the moles. So it's simple ratios. So we know that 25 cm3 H contains how many moles? It contains 0.00254 moles. So if you have 250 cm3 of H, which was our original solution, that would contain how many moles of FeSO4? So using ratios, this would come out to be equal to, if you crisscross and cross multiply the moles of FeSO4, would come out to be equal to, it's going to be equal to 0.00254 into 250 divided by 25, which is basically equal to 10. So the amount of moles is going to be 0.0254 moles of FeSO4. So in this flask over here, you have 0.0254 moles of FeSO4. So that's the quantity of moles of FeSO4 in this 250 cm3 larger solution. Now remember that all these moles of FeSO4 are coming from this hydrated salt of FeSO4.xH2O that was dissolved. So all these moles of FeSO4 are coming from there. So now he's asking, use your answers to calculate the mass of FeSO4 in the original sample of FeSO4.xH2O. Now you have the moles of FeSO4. The moles of FeSO4 are 0.0. You can use the formula moles is equal to mass divided by the molar mass, mR. Now the moles are given, which are 0.0254. We've already calculated the moles. The mass is unknown and the mR is also given. It's given over here that FeSO4 has an mR of 152. So using my calculator to figure out the mass of FeSO4 in the sample, the mass of FeSO4 is going to come out to be equal to 3.86 grams. So that is the quantity of FeSO4 that's present in this flask, and all this FeSO4 is coming from this hydrated salt that was added over here. So let's add that over here. The mass of FeSO4 in this salt is 3.86 grams. This was the total mass of the hydrated salt with the water in it. So in the next part, using your answers to A and G, calculate the mass of water in the sample of FeSO4.xH2O. So you had 6.96 grams of the salt. Now you know that 3.86 grams is FeSO4. So what is the quantity of water in it? So I just need to subtract the two values. It's going to be 6.96 grams minus 3.86 grams, which is the mass of FeSO4. And this here is the mass of the total salt with the water in it. And if I subtract the two quantities, the answer that I'm going to get is going to be 3.10 grams. So 3.10 grams is the mass of water in this hydrated salt. Now in the next part, Using your answers to H, we're now doing part I. So using your answers to H, calculate the number of moles of water in the sample. So we know the mass of water. Moles of water would be moles is equal to mass divided by the molar mass. So the mass is 3.10 grams. You have 3.1 grams of water, and I'm going to divide it by the molar mass of water, which is going to be 1 plus 1. That's 2 hydrogens plus 1 oxygen. So that's 16. So this is the MR of H2O, and the answer that I'm going to get is going to be 0.0172 moles. So that is the quantity of water in terms of moles. Let's fill this. Let's write that over here. 0.0172 moles. Let me just correct the answer. It was actually 0.172 moles in my calculator. So it's the moles of water are 0.172 moles. Now moving to the last part, he's asking us to find, using your answers to F and I, calculate the value of X in FeSO4.xH2O. So basically, we need to find that for 1 mole of FeSO4, how many water molecules would be attached to it. Now we can find the moles of FeSO4 and the moles of water. We need to find the ratio, and we need to figure out for that how many moles of H2O would be connected with 1 mole of FeSO4. Now we've figured out the moles of water in the hydrated salt. They were 0.172 moles. So there was 0.172 moles. So that is using the answer in part I. And if we move to the previous part F, he's asking us to what did we find in part F in the previous page. We were able to figure out the moles of FeSO4, which were 0.0254. So they were 0.0254. In the salt, the moles were 0.0254. So I know the ratio. In the hydrated salt, 0.0254 moles are present and 0.172 moles of water are present. Now I need to figure out how many moles, if you have 1 mole of FeSO4, then how many moles of water would be present with that. So using simple ratios, X would be equal to 0.172 into 1 divided by 0.0254. And solving this on my calculator, it's going to be 0.172. So 0.172 divided by 0.0254, and the value is approximately equal to 6. The value that the calculator is giving me is 6.77, rounded to 3 significant figures. And remember that X over here was initially, the question stated that X was a whole number. So assuming that we had some errors in our experiment, we're going to round this value off to 7. So since it's a whole number, so the formula of this salt, the hydrated salt, would be FeSO4.7H2O according to our experiment and according to our calculations.